All right, I'm reading in the Pilot's Handbook of Aeronautical Knowledge. This will be Chapter 3. This will be page 3-5, rotating cylinder in a moving fluid. When the cylinder rotates in a fluid that is also moving, the result is higher circulatory flow in the direction of the rotating cylinder. By adding fluid motion, the magnitude of the flow increases. The highest differences of velocity are 90 degrees from the relative motion between the cylinder and the airflow. Additionally, as shown in Figure 3-4, at point A, a stagnation point exists where the air stream impacts and impinges on the front of the airfoil surface and splits. Some air goes over and some under. Another stagnation point exists at B, where the two airstream rejoins the resume at identical velocities. When viewed from the side, an upwash is created ahead of the airfoil and a downwash at the rear. In the case of Figure 3-4, the highest velocity is at the top of the airfoil with the lowest velocity at the bottom. Because these velocities are associated with an object, in this case an airfoil, they are called local velocities as they do not exist outside the lift-producing system, in this case an airfoil. This concept can be readily applied to a wing or other lifting surfaces. Because there is a difference of velocity above and below the wing, the result is a higher pressure at the bottom of the wing and a lower pressure on the top of the wing. Let's look at some grooves. Okay, so we'll go here. So on page 3-7 to continue. This low pressure area produces an upward force known as the Magnus Effect. The physical phenomenon whereby an object rotates affects its path through a fluid to include air. Two early dynamicists, Martin Kuta and Nikolai Joukowsky, eventually measured and calculated the forces for the lift equation on a rotating cylinder, the Kuta-Joukowsky theorem. To summarize the Magnus Effect, an airfoil with a positive AOA, angle of attack, develops air circulation about the upper surface of the wing. Its sharp trailing edge forces the rear stagnation point to be aft of the trailing edge, while the front stagnation point falls below the leading edge. So, Bernoulli's principle of differential pressure. A half-century after Newton formulated his law, Daniel Bernoulli, a Swiss mathematician, explained how the pressure of a moving fluid, liquid or gas, varies with its speed of motion. Bernoulli's principle states that as the velocity of a moving fluid, liquid or gas, increases, the pressure within the fluid decreases. This principle explains what happens to air passing over the curved top of the airplane wing. A practical application of Bernoulli's principle is the Venturi tube. The Venturi tube has an air inlet that narrows to a throat constricted point and an outlet section that increases in diameter toward the rear. The diameter of the outlet is the same as that of the inlet. At the throat, the airflow speeds up and the pressure decreases. At the outlet, the airflow slows and the pressure increases. Since air is recognized as a body and is accepted that it must follow the above laws, one can begin to see how and why an airplane wing develops lift. As the wing moves through the air, the flow of the air across the curved top surface increases in velocity, creating a low-pressure area. Although Newton, Magnus, Bernoulli, and hundreds of other early scientists who studied the physical laws of the universe did not have the sophisticated laboratories available today, they provide a great insight into the contemporary viewpoint of how lift is created. So there was those stagnation points. Leading edge stagnation, trailing edge stagnation, and Bernoulli's principle with the Venturi tube, the inlet and the outlet, and the constricted point, the throat. So pressure increases and speeds up here, decreases out here because it's bigger now. Okay. we'll hold off there. All right, that was page 3-7, Bernoulli's principle, and yeah, the rotating cylinder and moving fluid. Watch out for that one.